has his short biography on his own website, so I don't even have to think of anything. But yes, he's a Banting postdoc fellow at Harvard, working with Misha Lukin and Michael Gullens. Are you actually working with Michael also?
Yeah.
That's good.
Yeah.
He earned his PhD in 2024 from the University of Waterloo with Ray Laflamme and Nicole Younger-Halpern. Were you Ray's last student, or did he have some more?
So there's graduated that same
Okay.
PhD.
I see. Okay.
There's master's students who've since graduated.
I see. Yeah. He co-wrote a book about how to build quantum computers, which is pretty cool. And I guess he'll tell us about how to build a fault-tolerant quantum computer. So please give him a hand.
That's okay? Hello? Hello? Okay, great. Okay. So yeah, so if you've okay, maybe I'll just say that again for the recording. So if you're here, it's probably because you've heard about the potential of quantum computers, maybe for drug discovery or cryptography. And there's very exciting potential, but we can't currently reach that potential because error rates are too high on current hardware. So if we look at the road to these exciting applications, we're currently in the regime of about 10 to the minus 2 to 10 to the minus 3 error rates, but really we'd like to be more in the 10 to the minus 12 regime. And there's still some improvement that can be made with hardware, but really we don't expect at all to be able to get to 10 to the minus 12 error rates with just physical hardware improvements. And this is why when quantum computers were first proposed, it was actually just thought it's going to be impossible. Like we just cannot get to the error rates to ever do anything useful with these machines. But that was before quantum error correction. So quantum error correction is the only known realistic route to sufficiently suppress errors to reach these interesting applications. So how does quantum error correction work? I think there's only really 4 things you need to know to have a really good understanding of quantum error correction. So one is that we store information non-locally across qubits. So here if we have this can be a single physical qubit. This is a 2-level system in which I encode quantum information. I can encode it across the correlations in many physical qubits. So each of these circles would be one physical qubit that I've entangled in some fashion. And this whole block is now one logical qubit. So before on my physical bit, I would need a single poly Z error to occur to have a Z error. Where on a logical qubit, I actually need to have, so in this case, it's the distance 5 code because it takes 5 physical errors to get a logical error. And same with X errors. The second important thing is that we have our information stored in these logical qubits, but as we're doing a computation, we want to check if errors have occurred. But we can't measure our state exactly because that's going to collapse our wave function. So instead, we take these partial measurements that allow us to keep our logical information intact, but identify whether or not errors have occurred. So this operator here is a Z operator on these 4 sites. As long as that outcome is +1, I assume no physical errors have occurred. And then similar here, if these 4 X operators are +1, no physical error has occurred. So I can take these partial information from the system, without damaging my computation. And finally, I think the one I find actually the most exciting and most interesting is that the errors are discretized. So I think when you first hear of quantum computing, I think the natural instinct is to think it should be impossible. Because we're doing these continuous evolutions, right? We want to do unitary dynamics. And if we've heard of analog computation, we know, okay, error correction is incredibly difficult with analog computation, so much so that it's not like a realistic route for computing. So how come it's possible with quantum computing if we have analog evolutions? And the answer is that the errors are discretized. We have some continuous physical rotation that'll happen in real space, but then we go and do a stabilizer measurement, and that collapses the error to a set of one of many different discrete possibilities. And that's what enables us to correct these errors. And finally, we want to be below something called the threshold. So here I have the physical error rate, and then the effective logical error rate. So this is the error rate you'd have on the physical qubits. This is the error rate you'd have on the logical qubits. We want to be in a regime where increasing the distance of our code gives us better and better performance. You can think of it as, if I have a very small code, I should get some suppression, and as I scale the size of this code to be a bigger square, I should get more error suppression. And that will happen if I'm below the threshold. So you want to be below threshold, and that depends on the given code and the decoder, amongst other things. So this is the theory of quantum error correction. And honestly, it sounds quite complicated in theory. You might think, okay, how are we going to realistically do this in the lab? But over the last year, there's been very exciting QEC primitives demonstrated in practice. So there was this paper by Google. Anyone invest in quantum index funds by any chance? No? Okay. If you saw a sudden surge last year, that was because of this paper. So if you ever want to make, I think right now a great short-term strategy to make money is to just short quantum index funds whenever they become, no, this is recorded, I won't say that. There's some people with company, but okay, maybe I made some money doing that. But anyways, so here using a superconducting platform, they were able to be below threshold. And so this was with a quantum memory experiment. And we've seen very exciting things with trapped ions as well, where here they're able to do demonstrations where the logical error rates were better than the physical error rates. With neutral atoms as well, we've been able to do logical algorithms in the past, where we've also seen the benefits of using logical qubits over physical qubits. So this is with this IQP sampling, which, okay, the short of it is that there's a class of circuits that are hard to sample efficiently, we believe classically, but we can do them efficiently with a quantum computer. And so we're able to do that in the lab and see a benefit of doing it using logical qubits. And there's many other works that have been along these lines with different hardwares like bosonic qubits. So we know we need QEC. We understand how it works, and we've seen the primitives in practice. Really, the frontier of the field now is reducing the overhead of quantum error correction. So much so that I'd say it's probably one of the most important questions in the field of quantum computing is understanding how we're going to do this. Maybe to drive that point home, there was a study, there was this review article where essentially they were estimating the cost of how many qubits would we need and what error rates would we need and how long would we need to run quantum computers to be able to see quantum advantage. And to simulate a very modest molecule, right now with our current approaches, would take on the orders of millions of qubits and years of runtime. So we're not going to spend years in the lab to do a single experiment. So we need to reduce the overhead, and there's been steady progress in this regard, but it needs to continue. Okay, this is my introduction to quantum error correction. It's probably a good point to pause and take questions, if there are. No. Okay, feel free to also come back later. You can ask me a question. Maybe people know more about quantum error correction than I knew. Okay, so what do we do here? So in this experiment, we implement all the elements of a universal fault-tolerant quantum computer in the same experiment using the same hardware. And in doing so, we can better understand the underlying physics of quantum error correction with the hope that, as we better understand this, we can identify other mechanisms for reducing the overhead of QEC. So in particular, we did the below threshold quantum error correction experiment. So we show how increasing the distance improves your logical error rates. And two really, I think, interesting physical effects that come up here is we can really see the role of dissipation in quantum error correction, despite the algorithms being unitary. We can clearly see the Zeno effect. So I'm going to explain what that is and point that out. We then did fault-tolerant gates with quantum error correction. So the threshold experiments so far have been with quantum memories. So we're just preserving the logical information and doing so at different distances with repeated rounds of quantum error correction. But we actually want to do algorithms in a lab. So we have to be able to do the gates fault-tolerantly. And fault-tolerantly means that the errors essentially don't spread beyond what we can control. And what's cool here is we can see how the detectors we use for identifying errors can be interpreted from a cooling heating perspective as having some type of ambient heating that decides how often we should use detectors. So I think I'll explain that. We demonstrate using logical magic. And so I think a really interesting question someone can ask about quantum error correction is, when do you actually need entanglement? So let's say I give you a bunch of physical qubits and I lie to you. I say these are logical qubits, but they're actually a bunch of physical qubits that haven't been entangled. Under what algorithms can you tell the difference? Under what algorithms can you not? And the answer to that actually comes down to contextuality and logical magic. From there, we want to be able to actually run any algorithm. And so with logical magic, we get a universal gate set. We get the ability to do gates that if we combine them in different ways, we can do arbitrary algorithms. But we're starting from a discrete gate set and we want to do arbitrary angles. How do we do that? We demonstrate how to do that. And the trick is essentially taking a tool that's been used a lot with photons, measurement-based quantum computing, at least proposed for photons, and applying it to neutral atoms. And we can see how we use that to break the Easton-Nail theorem, which I'll also explain. And then another element of quantum computing is maintaining a constant entropy as you run a deep circuit. So we want to be able to run arbitrarily deep circuits, but we can't let the entropy build up to the point where we can no longer run useful algorithms. So what strategies can we use outside of just traditional quantum error correction to maintain constant entropy? And we're going to see how we can initiate types of cooling cycles to be able to do that. So this is a broad overview, and I'll go into each of these in a bit more detail. And feel free to stop me at any point. I really enjoy questions and discussion. Okay, so I should have explained at least briefly what the hardware is we're using. So here, this is all done with neutral atom arrays. So the qubits are the hyperfine states of 87 rubidium trapped in optical tweezers. So here, this is an actual image from the experiment. So each of these dots is a different atom trapped in individual optical tweezers. Here we're using a zoned architecture. And the importance of that is essentially there are different laser beams connected or pointed towards these different regions. So in the entangling zone, it's where we have to have our Rydberg interactions. So we need a certain set of hardware to enable that. But in the storage zone or the readout zone, we don't do entangling gates, so we don't have to place that architecture there. And that helps improve the lifetimes of the other qubits. And it's just a nicer picture of it. So the coherence times are on the order of about 2 to 3 seconds right now. And then this is, say you're first and you're proposing experiments, what would you use? You would go to figure out what are the 1 qubit, 2 qubit, and measurement times to run in the lab, and then what are the error rates? So here are the error rates for each of these. And then, just like I said, so the interaction with 2 qubit gates is done by mediating this Rydberg interaction. Okay, so what are the strengths of this hardware? So I'm really a believer in that there's many hardwares right now that should be pursued because they all have different strengths that we can leverage for different tasks. So what are the strengths of neutral atoms? One is non-local connectivity, which quantum error correction loves, because being able to make codes and not have to worry about the connectivity of stabilizer checks is really a theorist's dream. And then efficient parallel control. So what this is here, this is one patch of neutral atoms that's been prepared in a logical state. This is a surface code state. You don't need to know what that is, but this is one logical qubit. We can pick up the atoms, move them over on top of the other atoms, and then apply individual gates across these pairs of atoms. And what that does is it creates a logical gate. It's called like a transversal C0. But it's a controlled NOT gate on the logical level made up of parallel physical controlled NOT gates. And this freedom to move around allows us to do really cool connectivity to create really interesting codes. So of all the videos, this is probably my favorite. because it kind of reminds me of like synchronized swimmers moving around. So here the atoms are being moved around in pairs and being entangled to create, here it's a hypercube connectivity. It's to create a particular type of quantum code. And this is like greatly slowed down. Like the movement times are much faster than this. Like to move a 2-qubit gate, like for one of these, it's 400 microseconds. So this has been slowed down so we can see it. Okay, and one of the other strengths, and one of the reasons I think it gets a lot of publicity is we have many qubits in one array. And there's trapped ion people in the audience, so I'll say that all these architectures will need to learn how to connect their arrays together. So it's great you have a larger single array, but a question that the field of neutral atoms will also need to address is how do we connect these arrays together to scale even larger? So even though the numbers are large, there are still limits. Yeah. Okay, and so if you've already heard of this hardware, you might have heard about the measurement problem we have. So the way we used to do measurements is we take qubits in the one state and we would just eject them from the trap, and then we would image what's left. And if the qubit was left, it's a 0, and if it's not there, we assume it was in a 1 state. What is now done is you can use a 1D optical lattice to pin one of the atoms in place if it's in the 0 state. Then you move the other atom now over. So if it's in the 1 state, it moves. And you then take an image of the two. So we can now do a state resolved readout that's non-destructive. And we can also reuse atoms. So before we do a measurement, we lose half the atoms. I mean, that's obviously not scalable. Here we can reuse the atoms. So here's an image of doing Rabi oscillations. So if you're on the left, you're a 0, on the right, you're a 1, and you can oscillate back and forth. Maybe I can pause here and ask questions about the atom. So I should also say, like, if it's a question like, what is the laser frequency? I'm not in the lab, but outside of those nitty-gritty questions, I think I can answer them. Yeah. Oh, right. So it's literally like a camera, like a photo. So if we can detect whether an atom is there. And so we have pretty much if it's in the excited state, we can just keep energizing it and like repeating that until the atom gets ejected from the trap, and then the 0 states are left. Yeah. 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 Okay, I don't want to give an exact number on recording without knowing for sure. So let me get back to you because a red dot from QERA might come on my head if I say that wrong. I'm not exactly sure. I think when I was doing simulations, I can give you a number of what they told me when I was doing numerics, and maybe I can let you know. Yeah. But it's a serious thing. Like atom loss is a serious concern, and you'll see in our plots, like it's like a prominent cause of error. And it's something that they have to really, really think about. And it's the strength of trapped ions. You guys don't lose your ions. Yeah. Okay, good. Okay, so let's get into some of this new physics. So one of my favorite debates, so again, my mom has soap operas, I have physicist debates. One of my favorite debates is Rolf Landauer and Peter Shor's. And so Landauer had this issue with quantum computing originally for the same reason I had mentioned, because of this analog computation. And correcting errors on an analog computer is just, we know analog computers are powerful, but error correction is too hard. And so Rolf Landauer had this issue that the computation is analog. And ultimately the rebuttal to this is that yes, but the errors are digital. So the picture I like to have in mind is, so you have some Hamiltonian and you have 3 energy levels. These are degenerate. So this energy level here is my ground space where my logical 0 and my logical 1 qubit live. And I can have some superposition, some wave function at that level. And then over time, errors occur. And these are continuous things. Some excitations happen. My system warps in some way. But then when I go and take a measurement, I collapse the wave function back into the possibility of either having not had an error at all, or being the same state it would have been had it not had an error at all, plus some discrete error I can then correct. So the measurements project me back into the case of having done the exact infinite precision evolution up to a discrete error. Yeah. So maybe a picture to have in mind is you have your logical subspace, you can evolve in it analog, and then errors will map you to this same evolution in a orthogonal subspace. And so on the logical level, what we have is a coherent unitary evolution, where on the physical level, we have dissipation. So we do measurements to identify these like excitations, these errors that occur, and then the measurements are a dissipative process. And then we can go ahead and track those errors and correct them. And so this is really nicely connected to the Zeno effect, if you've seen that before. So here I have a state evolving where I don't measure it at all. Here I measure it at some frequency, and here I measure it all the time. See, the measurements are projecting the system to different states, and if I'm measuring often enough, the system is not changing. And so we actually can see this effect when we do stabilizer measurements for quantum error correction in the lab and see how the repeated measurements actually suppress errors. Okay, so how do we see that? We're going to start with doing a distance 5 surface code experiment. And then we inject coherent errors. So we're going to break this evolution into 20 time steps. And at each time step, do a global rotation on all the qubits. And then we measure at the end the probability of the +1 outcome. If we're initially in the 0 state, we measure the expectation value of Z. If we're initially in the plus state, expectation value of X. And now we're going to do repeated rounds of quantum error correction. So for the surface code, every check needs 4 2-qubit gates. So they come in between these different errors. So you can have 1 check, 2 checks, 5 checks. This is what it looks like in the lab with the qubits. We have the data qubits in blue, the in silico qubits in orange. What we do here is we can tune the amount of error. So if you have no errors, the extra QEC rounds don't help you. But as you increase the errors, you can see the physical errors, the logical errors get worse. But the repeated rounds of quantum error correction suppress the logical error. So again, increasing physical error increases logical error, but repeated rounds of QEC suppress the logical error. Yeah.
This isn't just one Zeno effect, you're actually doing quantum error.
So excellent question. The next picture. So here there's 2 parts to it. So part of the suppression comes from the Zeno effect, and we see that when we discard the ancilla. So we do this in 2 ways. One, we do the stabilizer measurements and completely disregard the ancilla. And we get this suppression here in light blue. And that's just a Zeno effect suppression, which I thought was like super cool. We could actually see that in the lab. I was like really excited when that actually worked. And then you can also track the ancilla to be able to track the errors, and then in the end, correct the errors. So then with the error correction, we get the scalable suppression. So that's what these distinctions are. So these are like 2 mechanisms that underlie the Zeno effect, and then tracking errors and decoding that underlie error suppression and quantum error correction. Yeah, no problem. Yeah, no problem. Okay, so what do we do with this? So we repeat this experiment with a distance 3 and a distance 5 surface code. And then we see that as the distance increases, the logical probability error goes down. These different plots correspond to different types of decoders. The decoder that performs the best is the machine learning decoder, where we integrate loss. I think a really interesting question right now. Okay, a question we get a lot is, what is the role AI can play in quantum? And I think we're looking for like concrete, tangible examples that we can go further on. One that we've really seen benefit of is machine learning decoders. Currently, they just, in practice, outperform our best algorithmic decoders. And I think an interesting dynamic that is at play here is that we need AI expertise to be able to program these things. But it's really also physics expertise to know, to think about like the design principles here. So as you can see, so this is the machine learning decoder. When we essentially explain to it, to some extent, the knowledge of the loss in the system, that these are loss errors, they occur with this frequency we see in the lab. And then here's the machine learning decoder trained without that. And you can see how much better it performs when we use those physical insights. And so, yeah, so the threshold depends on the decoder. And yeah, like I mentioned, machine learning one works best. So we're currently about 2 times below threshold. And here we have this plot where we scale over different amounts of mean qubit loss. So what this means is here we have the regime. So yes, okay, this maybe indirectly to some extent answer some of your question. We have about 3% qubit loss. These are the logical error rates. And then we can sample over subsets of experiments in which we had less and less qubit loss and average over those. And if we scale the qubit loss back, again, post-selecting on the experiments that had a lower percentage loss, we can get better obviously error rates. I think there's one more thing. Oh yeah, and this is the wonderful decoding team. I think these four did a ton of work on the decoding front, and I acknowledge them in the end. Okay, I'm going to put 2 slides up and take questions because I'm super behind schedule. Okay, so I think a very natural question to ask now is we saw the plot of increasing quantum error correction. And so you can ask, is more quantum error correction always better? The Zeno effect is it's suppressing the errors to some extent. Why don't we just measure all of the time? So quantum error correction is a mechanism to decrease entropy. Like, we reduce uncertainty in the state of our system. So in one respect, it's like a cooling agent. But the measurements are noisy, and the coupling of the ancillary qubits to the system is noisy. So every time we do a round of quantum error correction, we're introducing some error into our system. So I think that an intuition to have here is if you took a perfectly cold system that's below whatever this can cool to, and you introduce quantum error correction, you would only be making things worse from this like passive ambient heating. But if you're above a certain amount of error, then this quantum error correction will actually benefit you, and it's in your favor. And it depends on the error rate of your system. Yeah.
Stay in the logical code space. Why does measuring a stabilizer ever affect you at all?
So the measurement itself can introduce an error, because to do the measurement, you have to couple it to the ancillary qubit, and that coupling has an error rate.
Okay, not the ideal measurement.
Not the ideal, exactly. Yeah, exactly. Yeah.
Fundamental, the temperature.
Exactly. Yeah. So and maybe just to put on a microphone. So yeah, if the measurements were ideal and noiseless, then we wouldn't get this heating effect. But it's because they're not that we have to temper how much quantum error correction we do, depending on our algorithm and error rates. So I think this is a really interesting insight. And it raises the question of the optimal rate for an algorithm. So one way that we study this is in the context of doing transversal gates. So again, these are logical gates that we do with a bunch of physical gates. So you can do, here we do some n rounds of a logical gate, a single round of quantum error correction. I want to stress it again, 1 round. I think people often think you need order D rounds for transversal gates, so we do 1 round. 10 logical qubits again, QC, we repeat. So this is what the circuit looks like. We have 2 patches, bring them over, do the gate, and separate. Another scheme that's used more typically in superconducting hardwares, because they don't have the ability to move qubits around, is lattice surgery. And lattice surgery works by bringing in ancillary qubits. And then we do parity check matrices along the axis of the ancillary qubits that we brought in to entangle. And then the measurements play the role of entangling the 2 qubits. And we repeat those measurements. And so to be clear, in both of these settings, measurements play a role. It's a different role. In lattice surgery, the measurements mediate the interaction, where with transversal gates, the measurements are necessary for doing the quantum error correction and measuring the measuring the errors on the ancillary qubits. So here we had different amounts of measurement errors, and lattice surgery depends more on these measurement errors. So we see it get worse as we increase the amount of error, where the transversal CNOTs don't. And I think importantly, what we can see in this plot is what is the optimal amount of CNOTs per round. So here we can change how many CNOTs we do before we do a round of quantum error correction. And in this experiment, the sweet spot was around 3 CNOTs. And so why 3? It's actually somewhat intuitive from the surface code. So in the surface code, each of the stabilizer checks involves 4 CNOTs. So it costs you 4 CNOTs to do a round of quantum error correction. So it kind of makes sense that you wouldn't do, less than that before, doing a round of quantum error correction. So the sweet spot matches roughly with the number of CNOTs in the stabilizer measurements here. But again, this depends on the error model as well and the circuit that you're going to run. Okay, maybe this is a good spot to stop about this and take questions. Yes. Yes, sure. So with transversal CNOTs, these are probably what you learn in like a textbook course on quantum error correction. So you have the logical, can I draw somewhere? Okay, that's okay. So you have just go over here. Okay, I'm too weak to open a marker. Here we go. So you have your circuit. and then these are three physical qubits. And you do these three physical C naughts, and this will be equivalent to doing one logical C naught. Oh, this is good? Okay, cool. Yeah, no problem. Okay, great. Other questions? Yes, please. Yeah.
I think, but thinking about your Zeno approach, and wanted to ask, if you imagine taking the sort of infinite limit of rapid Zeno measurements and just turn it into a Hamiltonian based on the stabilizer operators, so that you create a gap between logical space and the rest of the space. Does that have the same effect, to make a large enough gap between all logical space and the others?
So that the gap effectively is too large for the errors to cause excitations on like some reasonable scale. So yeah, that's right. So I guess that really would just depend on, yeah, if the error rate is sufficiently low. So I think if you do like an angle theta rotation, so the plot I had before, where we had like an angle theta rotation, where you get suppression with the Zeno effect, the Zeno effect suppression goes as order theta squared. So we do need the theta to still be small. So if it's sufficiently smaller than the gap, then I think that should be fine to work. But I think engineering a gap that large, I think with a qubit system, I imagine you would need quite a few qubits. Yeah, okay. I guess, yeah. Yeah, right, yeah. But no, I think that could be, it's an interesting direction. I think, yeah, one of the things I really love about, these physics of QEC experiments is it opens up all these really interesting theory questions that you can just, eat with for a long time. Yeah. Okay, great. Okay, let me go to a really cool, I think, thought experiment. So say I have some logical qubit, and I do a global phi rotation. So I'm doing some angle, some arbitrary rotation z on each of the physical qubits. So this could be like a transversal gate. So if I go back to this picture here, instead of C naughts, just imagine one of these blocks. I'm not going to try to open that again. Open one of these C naughts, and I do some small angle rotation here, small angle rotation here, small angle rotation here. I could get, if it's a transversal gate, I would get that same angle rotation on the logical qubit. That would make it a transversal gate. So what I can do is I can do these rotations on each of the physical qubits, and I can see the effect on the logical space. So if I start with a bunch of unentangled qubits, you can start imagining you have a single physical qubit, and you do this, you're just going to get Rabi oscillations, okay? But now if you have multiple qubits, you're going to multiply, this function will just be cos theta to whatever power of the unentangled qubits you have. But what's interesting, I think, about this plot is that if you do a 90-degree rotation on the physical level, that corresponds to physical S gates on each qubit. You've done a logical S gate on the qubit. And then at 180 degrees, you would have done a physical transversal Z gate, and you get a logical transversal Z gate. This is an example of a broader effect where if you initialize some system in a Pauli states, and so these are like states that are classically simulatable, you run a Clifford circuit and you measure Pauli expectation values, the physical qubits will recreate the same measurement outcomes as the logical qubits. So you don't actually need to entangle your qubits and prepare the logical state if you're running this Clifford circuit and you're only measuring Pauli expectation values, which is what happens at this point, this point, this point, this point, and that point. So you can go and you can do this with an actually encoded, with say a 2D color code. Okay, I don't have time to explain what this is, but for those who work on quantum error correction, this is the color code I have in mind. And it has a transversal S gate. We do the same experiments, and we also get the stable plateaus at the same points. And these are the points where it has transversal gates. So I've already alluded to these points are the points we can reach with a Clifford circuit. We want to have magic. Magic is the things that are non-classically simulatable. So we run the same experiment with a 3D color code. Again, I won't explain what that is, but for those more familiar, this is the stabilizer structure. And I can do the physical T's to get a transversal T. What I find is these new plateaus emerge. And these new plateaus occur where you have a T gate. And these are the gates that you can't get to classically. And these are the gates that we can't fake with physical qubits that aren't entangled. And because we were here anyways, we did one experiment where we did the 3D color code with the wrong stabilizers. Maybe this is more of just a nugget for those who've studied the 3D color code before. You may have heard that to do the transversal T, you actually need the right stabilizers. It's not just enough to be able to track the errors. If you get the wrong stabilizers, you don't get the plateaus at the T gates, which is a signature of an effect where if we want to do magic, we need to have decoded first. We can't just track errors if we get to a point in the algorithm where we want to do a magic gate. Okay, that's a bit technical, but just for the QEC people. So yeah, we see in-block entanglement plays two very important roles. It's needed for magic. And even in the context of magic, you can't just track stabilizer signs. I'll put one more thing and I'll take questions. So we say that we need to entangle the code block to be able to get magic. But we also know that, so if you've studied Bell tests before, you can't just do a measurement on any axis and get a violation of a Bell inequality. You have to do these measurements at these large angles away from the orthogonal axes. So like 45-degree rotations would be to get the largest Bell inequality violation. And that angle rotation is what corresponds to a T gate. So say I have two logical qubits, and I want to prove that they're in a Bell state. I can go and I can do a logical XX measurement, a logical ZZ measurement, and I can verify that they are a logical Bell state, even if I don't do any magic, even if I have the entanglement structure wrong in my code. But if I actually want to have magic, I need to actually entangle my qubits. And so we did this experiment where we take two logical qubits and when we use a T gate, we actually can get a maximum Bell inequality violation. But without the T gate, we're not able to do that. And the experiments that don't have the logical in-block entanglement, you can spoof this. You can get kind of like a fake Bell pair, a fake logical Bell pair that doesn't actually violate the CHSH inequalities. So I thought that was super cool. Okay, maybe I'll pause here and take a question. Yeah. Yeah, so decoding is very challenging. And as we scale, I think one of the big open questions is how are we going to efficiently decode? Because we also need to do it fast. Once we get, so if you're only doing a Clifford circuit, if you're only doing like if you're only doing a Clifford circuit, you can just track your poly errors through your algorithm, and then you're fine. But once we go to do a magic gate, then we actually need to decode live, and we actually have to correct the errors. So for that point, yeah, we need very fast decoders. Ideally, like something you do kind of on chip that immediately gives you the answer. Yeah. Yeah, so here so here we use a machine learning decoder, and we can do that at the current distances we have. Like we can train machine learning decoders, but at higher distances, that's like an open question. Like how are we going to be able to scale machine learning decoders to higher scales? I was at UMD and I asked, I wish I remember his name, but someone introduced me to someone who's like, oh, this is the world expert on classical decoding. So I asked him, I was like, why don't we use machine learning decoders classically? Or I guess, and his answer was like, well, we kind of do to some effect. But for the most part, is we just have really good classical decoders. And I asked him, like, what do you think the future of machine learning decoding is? His opinion was, maybe it's good, I don't know his name, so I'm not quoting him on video, but he was saying he thinks we just need to develop better algorithmic decoders, that there's just, inherent limits here. But I think there's actually some very promising works, like one I'll mention at the end that came out recently, showing really some convincing results that machine learning decoders can be effective beyond the scales we've currently used them. Okay, for how long, how larger scales? Open question. Yeah. Yes. Or sorry. Yeah. Go ahead.
The T gate is
exactly. Yeah. So we have a transversal magic gate with a 3D color code. That's right. Right. Yeah, so the universality, which is combining Clifford with magic, that is very challenging. Here, the 1513 code, it doesn't have a transversal Hadamard. So you don't get universality because you don't have the Hadamard. But you do have C-naughts and you do have magic. So what you have to do with the 1513 is you have to inject Hadamards. With the 713, what you have to do is inject T-gates. So yeah, part of the result you have in mind is the Easton-Nil theorem, and then Easton-Nil theorem tells us with transversal gates, with unitary transversal gates, we can't achieve universality. But yeah, it's a very interesting property of this code. Yes. Yeah, that's right. So say I do my, yeah, let me take a step back. So I want to do a logical Bell experiment. So I want to prepare a logical Bell state. My fake logical Bell state is I never actually prepare the logical qubits. I just take a bunch of physical qubits and another bunch of physical qubits, and I pretend they're logical qubits. On the other one, I actually go and encode them and create real logical qubits. So the fake one is I haven't actually encoded them. And when I don't encode them, I can't get these T-gate plateaus. And when I don't get those, I can't violate the Bell inequality. Yeah, thank you. Okay, good. Okay, oh, well, okay. So something I actually came across, for me, for the first time when we were writing the textbook, was measurement-based quantum computing. And so, there's people who are experts in the audience, but at a high level, what MBQC is you can take a circuit. So this is a very simple example, a one-qubit algorithm that looks like this, Z rotations alternating with Hadamard's. And you can either go through the math of it yourself, or believe me that this circuit here, starting here with the output here, has the same effect as this circuit above. Okay, so if I go through here, I'll do the Z rotation and then effectively teleport my state over. And the teleportation essentially brings with it a pesky Hadamard. So a Hadamard now appears here. I do the Z rotation, teleport another Hadamard, Z rotation. And that's how I get this circuit up here. Now, east and nil, which I just explained, with unitary transversal gates, I can't get a universal gate set. But what I can do is I can go and repeat this MBQC experiment with logical qubits. So now this, and instead of just doing any angle rotation, I'm going to do a T gate. So I'm going to do a T, H, T, H, T. And I just pick up this circuit and I replace it with the logical analog. I'm going to use the 1513 code, as was pointed out, as the transversal T gate. The teleportation is going to force on me a Hadamard. I'll do another T gate, another Hadamard, another T gate. T and H together can synthesize arbitrary angles. So now I've realized a universal gate set. So if you first look at this circuit, you might think something is wrong, because everything here looks transversal and everything here looks unitary. But I mean, they're going to see the measurements are actually what breaks it. So with the measurements, we can actually get the universal gate set using MBQC. So here we do the T and then another Hadamard, another T, another Hadamard. And if you take this circuit, it looks very similar to Hadamard injections. So if you just write out the MBQC circuit and you do repeated Hadamard injections, it looks like this, effectively the same thing. Except with the Hadamard injection, sometimes you go to the trouble of injecting the Hadamard, so you stay on the one logical qubit. But we just relax that freedom and we allow ourselves to move down. And so again, we're seeing with this effective unitary dynamics on the logical level, but the underlying physics that's enabling it is dissipative. We have measurements that are dissipating theirs. Okay, so with T and H, we can go to the lab and actually do this. And we can implement the Solovay-Kitaev theorem, which says we can synthesize arbitrary angles to precision epsilon with log 1 over epsilon gates. So this is, you can imagine looking at the block sphere from above. So that would be the 0 state, plus, minus, plus I, minus I. So there's no T gates. We can only move between the points you can access with the Clifford circuit. You have T's. These are all the points we could access. This is experimental data, but the error bars are too small to see here. With 2 T's, we cover more of the sphere. And then with 3 T's, we see more of the sphere. And you can see the error bars a bit better here now. And we can go and we can see what is the average separation. So if I pick some random arbitrary angle I want, on average, how close can I get to it? We get closer and closer as we increase the number of T's. And fitting the data, it scales nicely with the expectations of Solovay-Kitaev. Okay, I should probably take questions. Okay, any questions about this slide? Yes. Yeah, the last one, oh, sorry, this one, there should be error bars here that are not here. That I don't know, but that I can. Yeah. Yeah, so well, I guess, yeah, so it depends on how well we can do like these injections, and they are going to grow. I would say one takeaway from this that we had is we just need better ways to synthesize arbitrary angles. Like if we really depend on Solovay-Kitaev, at least in the near term, we're kind of toast. Like we need some other schemes, that I think on current hardware effectively perform better. One that's really interesting that we've been looking at is this like star scheme, where essentially say, okay, forget fault tolerance altogether for a second. Let's just do the arbitrary, like let's do a logical rotation. So if our distance is 3, let's do a ZZZ evolution on the physical level. And it's not fault tolerant and it has some errors, but for arbitrary angles, for at least for small angles, it performs much better than any type of like gate synthesis we can do. So yes, yeah, the errors will grow. And I think until we have much better error rates, we need alternative schemes for arbitrary angles. Great. Okay, so I'm gonna squeeze in this last one here. So in an experiment, we have various types of entropy. So I think from a QI course, we're familiar with poly errors, and there's some uncertainty when we have a poly error. But also, and let's just take a second to look, see how that works. So on the logical level, when doing measurement-based quantum computing, this is the circuit we have, and we've seen we can do some kind of logical evolution. We can ask the question, well, what happens if a physical error occurs? So if a physical X error occurs on one block of the measurement-based quantum computation, it'll propagate through the CZ one further block, but then it becomes a Z error and it stops propagating. If it was a Z error to begin with, it would have never propagated anyways. So the poly errors in measurement-based quantum computing are inherently limited to moving two steps in the computation. So errors can't arbitrarily persist in your algorithm, which is super cool. And I think it comes from having this fresh ancillary qubits that we resupply to the algorithm. But we also have other sources of entropy, effectively atom heating and loss. So the atoms can heat up and get energized, and eventually that could lead to them being lost. Maybe they're already lost. But what we can do is we just put a fresh fresh logical block, excuse me, and we do the teleportation. It gives us an opportunity to replenish those qubits. So it's a different source of entropy that we can remove that isn't immediately captured in the tracking of poly errors. And so how do we use this? Imagine you want to prepare a 1D cluster state. And so here I have a bunch of qubits in the plus state. I have a chain of CZs. There's this notion, I think Isaac Trong calls this holographic quantum computing, where you take this qubit that you've measured that you're never going to use again, and instead measure it here, and then replenish and reuse that qubit here. And just keep building that. It's kind of like the picture of like a train moving. You take tracks from the back and putting them in front. It's kind of something like that. And we can go and we can convert this same circuit to only needing 2 qubits. And we take this qubit, we replace it with a logical qubit, and now we do these repeated rounds of CZ, measure, back and forth, back and forth. And so we did this in an experiment. Here, this is the decay of the logical correlations with time. So there are still errors. Computation is still not perfect. So we do have some decay of the logical Z errors. The decay of the ZZ correlations. But then you can see the physical errors, the correlations die off really quickly. So the physical errors don't seem to stick in the algorithm and indefinitely continue in the computation, where the logical Z operators do. So this is the underlying dissipation at effect, where we still have unitary dynamics on the logical level. And just to complement that slide, we can also go and do this again, but replace each one of these individual logical qubits with a 1D cluster state. So now we have a full cluster state. We can project onto a whole other cluster state to a whole other cluster state. And that way we can build a 2D cluster state in space and time. And so we do. So here we prepare these 16 713 codes. We initialize them in a 1D cluster state, teleport them onto the next block, on repeat to create a 2D cluster state in space and time. Okay, I'll just quickly show the video and then kind of wait for time. So here's preparing the 2D, so the 2 1D cluster states. We prepare 2 of them here. And then, we teleport the information onto that. And then now we take the block that we just used and we replenish the atoms. So the atoms that were lost can now get refilled. and then we repeat it again. And here's the experimental data from that. These are the correlations of the 2D cluster states, like the XEX correlations. And then we can see that throughout space, the fidelity stays about the same, but then over time, the reservoir starts depleting. So as we go to replenish more atoms, we're slowly running out of atoms because we don't have a method in this paper to continuously reload the atoms. So eventually the atoms get lost, we run out, and the fidelity as decays. And then here we have the physical errors. And okay, just for time, I'll throw up my last slide and take questions of everything together. So you can now imagine like a cooling model where you do some kind of computation, it heats up the system, you then teleport onto the next level. You can now throw away your hot qubits, reinitialize, refill loss, and then repeat again. So this thermodynamic picture seems actually quite useful in this neutral atom setup. So it's the first time implementing all of the elements of a universal fault-tolerant quantum computer. On the hardware side, right now, so this is, again, okay, a technical question beyond me, but for various reasons they explain in the paper, they expect to be able to move from 2 times below threshold to the 5 to 10 times below threshold regime in the near future. The group had another paper on integrating continuous reloading. So I mentioned that we eventually run out of atoms. This experiment, here we have a bunch of atoms, and then they're being continuously reloaded into the trap. And then, yeah, so we're continuously filling atoms. This paper didn't do gates yet, but here we demonstrate the ability to continuously reload atoms, which is, I think, the next step. So this was just published a few days ago. On the theory side, I think there's a lot of interesting questions. One is improving the scalability of ML decoders further. And there's a recent paper that I think makes really nice progress in that regard. There's many schemes for entropy removal. So if you're following, for example, now, there's these really nice schemes where you take an arbitrary Hamiltonian, you bring in ancillary qubits, and you can come up with a cooling scheme based on the Hamiltonian. In many ways, it has kind of a QEC flavor. So how can we integrate that with the current QEC is a question we're actively working on. We've seen we go through a lot of trouble to entangle qubits, whether it's through transversal gates, whether it's through lattice surgery. But qubits are inherently highly entangled, logical qubits are inherently highly entangled things. Can we also take inspiration from thermodynamics and recycle and reuse the entanglement in the code block for doing other gates? So we have a paper on that coming out like maybe in a month or so. And then this point that was really nicely raised about, how are we going to do these small angles? So say you want to do a quantum simulation and you want to do a trotterization, you want very small logical angles. What is the smartest way to get those on current hardware? Is it, non-fault tolerant approaches? Is it exploring different codes? It's a very interesting question that I think we'll need to answer to do quantum simulations logically. And I think lastly, there's a very evolving co-design landscape. So right now we're in a place where the hardware's strengths are dynamically changing and new codes are being dynamically developed. We need to identify tasks that maximize the benefits of each of these. And I think it's a really nice role theorists can play in the current frontier of quantum computing. And I want to thank this huge team that worked on this project. It's really amazing how well coordinated everyone is, and they can, everyone can, manage to work on large collaborations. If you're going to be teaching a course on quantum hardware, I guess buy my book. So yeah, and yeah, so I said last time I was here, I actually had to leave early because my son was about to be born. Last time I was here, he was about to be born. That's him now a year later. So I thought, nice tie back to the last time I was here. Okay, I'll take some more questions now. Thank you. Sure, yeah.
Back a bit, there was one where you skipped down in a little twisty curve. And
This one?
back to
Sorry, I should have numbered this maybe twisty twist?
No.
No.
Talking about reuse.
Oh, reuse of qubits, yes. Closer to the end. We will get there.
There.
Yes, oh, this one, yes. Yeah.
The little curve that takes you from the top line to the
Right.
third line. are you indicating that going for different blocks or it's
Yeah.
actually moving around or?
Yeah, so this you can at a first level just think of it from as a theory result that if you're ever doing a computation and you have some limitation in the number of qubits you have, if you can rewrite your algorithm in this like triangular shape coming down, then a qubit you measure in the very beginning of the algorithm, there's no point just having it hang around there. You might as well reuse it later on in the experiment. So you can just decrease, you can sacrifice qubits for depth. So it's essentially, the argument is more saying that these two circuits are equivalent, and the measurement outcomes you get from these measurements, and then the two at the end, will be the same measurement record you get from these qubits. So you could do that by like moving atoms around, or you could just have two qubits, and you could run the experiment, reset one here, and then just reuse the reset one. So it doesn't have to. Yeah, as long as you can reset it back to the right initial state, then you're okay. Yeah, exactly. Yeah, exactly. So this is just a theory result independent of that. That's right.